Any time you make a measurement in the real physical world, there is some uncertainty in the measurement. A scale has only so many digits or can be read to only a certain precision. A ruler can only be read to a certain precision and is manufactured to a certain accuracy. A ruler also changes dimensions with temperature and possibly humidity. A voltmeter has only so many digits, and a thermometer can only be read to a given precision. A responsible engineer will always estimate and indicate the uncertainty in any measurement. In addition, the measured quantities are often used to calculate other quantities. For example, the mass and velocity of an object are used to calculate the momentum and the kinetic energy of the object. Again, a responsible engineer will report the uncertainties in the calculated quantity due to the uncertainties in the measured quantities. Sometimes the things being measured or calculated are continuous or discrete functions of some other quantity. For example, spring force is a function of position or velocity is a function of time. The responsible engineer will plot not only the functional relationship, but also the uncertainty in the functional relationship. First, some definitions. Statistics posits the existence of a true value for a measured quantity, sometimes called the true mean or population mean, and is given the symbol mu. It's the value you'd get if you had an infinite precision ruler or weighed everyone in Southern California on an infinite precision scale and took the average. We almost never know the true mean. Also, if we had the table of infinite precision weights of everyone in Southern California, we could calculate how these values spread or distribute themselves about the true mean. One metric that characterizes the spread of these values is the true standard deviation or the population standard deviation, and is given the symbol sigma. Again, we almost never know the true standard deviation. Instead, we have to come up with a method to estimate the true mean and true standard deviation and make some guesses about how close these values are to the truth. We almost never know the truth, but we believe that it exists, and we make our best estimates of what the truth is given the limits of time and money we have at our disposal. Let's begin by making a set of measurements x sub 1 through x sub n of the quantities of interest. We calculate the sample mean, or simply the mean of these measurements, by summing them and dividing by the number of measurements. We call this sample mean x bar and use it as our best estimate of the true mean mu. Our goals are to determine the value of x bar and to determine how close x bar is to mu. If we knew the true value, we could calculate the error in each of our measurements as the difference between the measurement and the true value. The error is usually given the symbol epsilon. Again, the error, strictly speaking, is the difference between the measurement and the true value. So we would have the set of errors epsilon sub 1 through epsilon n. However, we don't know the true value, only the sample mean, so we calculate the residuals, which are the differences between the measured values and the sample mean. The set of residuals is then e sub 1 through e sub n. In other words, the residuals are our estimate of the errors based on the sample mean. The sample variance is calculated by summing the squares of the residuals and dividing by the number of samples minus 1. So it's essentially the average of the squares of the residuals. It is given the symbol s squared. Why n minus 1 instead of n? If we knew the true mean, each of the errors would be independent, but we're using the sample mean, which was calculated from all of the samples, so the residuals aren't independent. We lose a degree of freedom, essentially an independent equation, by using the sample mean, so we divide by the remaining degrees of freedom, n minus 1, for the sample variance. The true variance would be the sum of the squares of the errors, not residuals, divided by n, and is given the symbol sigma squared. Estimating the mean causes a minor but non-zero increase in the variance. A brief digression. Most people really dislike dealing with these quantities, and so don't devote much time to distinguishing between errors and residuals. So you will see both x bar and mu used for the sample mean, and both s squared and sigma squared used for sample variance. On those rare occasions when such distinctions are needed, it's up to you to determine what is being used. Anyway, the true standard deviation is the positive square root of sigma squared, given the surprising symbol of sigma, and the sample standard deviation is the positive square root of s squared, also known as s. S by itself doesn't answer the question of how close our estimated mean x bar is to our true mean, mu, but it is useful for other things. If we assume our set of measurements is roughly Gaussian, and we always assume our set of measurements is Gaussian, s can let us make some useful predictions. If we were packaging cereal and had set our automatic fillers to fill to a certain value and then we sampled and weighed some of the filled cups, we could get an estimate, how good we're not certain yet, of the mean or set point of the filler. But we would know that roughly 68% of the cups would weigh within plus or minus 1 standard deviation of the set point, and 32% would be further away than that. The number would give us a handle on how many complaints we might get from disgruntled customers complaining that there wasn't enough cereal in their cup. However, we're still left with the question, how close is our set of measurements to the true value? We'll use the standard deviation to answer that question, but we have a few hoops to jump through to get there. If we had the actual errors and not the residuals, we could calculate the standard errors as sigma divided by the square root of n with the symbol sigma sub mu. But then we wouldn't need to estimate how close our mean was to the true mean because we'd have the true mean already. So we'll use the estimated standard error, calculated as s divided by the square root of n, with the symbol s sub x bar. If the uncertainty in our mean is distributed in a Gaussian fashion, and really aren't they all, go look up the central limit theorem if you don't believe me, then if we took enough measurements, the true mean has a 68% chance of being within plus or minus the standard error from our sample mean. We typically write this out as a confidence interval. For example, we are 68% confident that the true mean is within plus or minus 7 thousandths of 42.000. The sharp-eared probably noticed that I said if we took enough samples. That raises the question. It does not beg the question. Go look up what begging the question actually means. How many samples is enough? Let's explore that question while contemplating a pint of Guinness. William Gossett was an employee trying to help Guinness with quality control and develop the statistical distribution for what to do with the standard error when the number of measurements was small. Quality control can drink only so many pints before their judgment becomes impaired. He published the paper under the name of Student, and the distribution has become known as Student's T distribution. In practice, it's used as follows. We calculate our mean and our standard error. We decide on a confidence interval and whether the true mean could be on either side or only one side of our calculated mean. We then go to the student's t-test table and use our degrees of freedom, n-1, as the row index, and 1 minus our confidence level as our column index. We use the two-sided table, the most common case, if the true mean can be on either side, and look up the value of t. Our measurement is then reported as the mean plus or minus t times the standard error with the confidence level given. You can linearly interpolate in the table if necessary. For example, x bar is 42.000 plus or minus 0.67 with 95% confidence. What are the implications of all this on your measurement making? You can make the mean of your measurements arbitrarily precise by taking a large number of measurements. However, limits of time and money mean that the number of measurements you make has to be limited. What are the trade-offs? The confidence interval, lambda, is the product of student's t and the standard error. For a given confidence level, t decreases asymptotically. This first plot is the value of t for 95% confidence given the number of measurements n. Notice that the decrease in t and hence the confidence interval from 2 measurements to 3 is by far the largest. That decrease is the reason for the dictum, take at least 3 data points. Beyond 3 points, the increase in accuracy due to the decrease in t exhibits the law of diminishing returns. The second figure is the confidence interval for 95% confidence as a function of n on a log-log scale. It shows, as expected, that for each 100-fold increase in number of points, you gain 1 significant digit of accuracy. You, as the engineer, need to decide how much accuracy you need given how long it takes to do measurements. To illustrate these points, this next video displays the calculated standard deviation in red, standard error in green, and 95% confidence interval in blue over a histogram of measurements as we add additional measurements beginning at 2 and ending at 10,000. The true mean is set at 0 and is indicated by a dark blue vertical line. The true standard deviation is set at 1. Note how large the confidence interval is for 2 measurements and how rapidly it decreases for 3, 4, and 5 measurements. Notice also that the true mean is always contained, at least 95% of the time, within the confidence interval, but that the confidence interval is rarely centered on the true mean. The sample standard deviation shows quite a bit of deviation, for small sample sizes, but becomes quite stable as the number of samples increases. As we pass 50 measurements, note the size of the confidence interval. From this size, it should decrease by roughly a factor of 3 as we pass 500 measurements, and a factor of 10 as we pass 5,000 measurements. Note also that the shape of the histogram, which didn't look terribly like a normal distribution to begin with, looks more and more like a normal distribution. The takeaways from this video are: 1. When measuring something, make at least 3 measurements, which gives you the greatest decrease in uncertainty per additional measurement. 2. Use the methods in this video to calculate your confidence interval from the estimated standard error and the student's t-value. 3. Report your results with the mean of your measurements, the confidence interval, and the confidence level, for example 42.000 plus or minus 0.067 and 95% confidence level. Video 2b shows an example of performing these calculations by hand. Video 2c shows an example using a spreadsheet, and Video 2d shows an example using MATLAB.